Okay, so our next speaker this morning is Wienhard, who's a professor of mathematics at the University of Heidelberg, and she has done really profound work in the kinds of representations that appear in finite dimensional higher Tychoid theory that was mentioned in the last talk. And in addition to this marvelous research, I must say that having collaborated with her on the GEAR network, she is really one of the main reasons that the GEAR network has been so successful. And so I just wanted to make that comment. And so now her title is Maximal Representations, Deformation Spaces, and Geometric Structures.
Thank you very much for this very kind, too kind introduction, and also for having the opportunity to talk at Bill's birthday conference. So it's a great honor and pleasure to do that. I'm not sure if there's any other mathematician who has influenced my mathematical life and also my mathematical career in the way Bill has. So I hope to pay you back a little. I want to somehow, with this talk, celebrate part of your work. Not all of it, of course. And I will focus on two aspects. One is surface group representations. So surface group representations. So I write also here homomorphisms from the fundamental group of a surface into a semi-simple Lie group, sometimes up to conjugation. And the other is deformation spaces of geometric structures. So we take a topological manifold M and endow it with a local homogeneous structure model on some homogeneous space X on which the group G acts transitively. So there's several relations between these two spaces, and we will come to that during the talk. I will focus on a more specific situation. Namely, I want to now first talk a bit about the space of homomorphisms for a special family of Lie groups G. So I have sigma, an oriented topological surface of negative Euler characteristic, and I will restrict the discussion to the situation of closed surfaces, just to simplify it. And I have G, not just any semi-simple Lie group, but I want to focus on semi-simple Lie groups which are of Hermitian type. And I will a bit later be even more specific and focus on a specific example of such a group, namely the symplectic group SP2NR. What is the, in a sense, defining property of a semi-simple Lie group of Hermitian type? It's that if I look at X, the symmetric space, G mod K, associated to G, this carries a G invariant closed 2 form. It carries a G invariant scalar form. So it carries a G invariant closed 2 form. Okay, there is actually a quite short paper of Bill from 82, I think, where with the title Characteristic Classes and Discrete Subgroups of Lie Groups, where he describes that whenever you have a G invariant K form on a symmetric space, you get out of this an invariant for representations by taking your representation, taking an associated equivariant map from the universal cover of your surface into the symmetric space X, pulling back this K form, and then if your manifold is K-dimensional, as we are here, you can just integrate it over the manifold. So there is a characteristic class or characteristic number which often goes now under the name Toledo number. It's also the first Chern class of some bundle. I don't want to go into more detail how it's defined. So if I have a representation of the fundamental group of my surface in such a Lie group of emission type, I can take this 2 form, pull it back, integrate it over the surface, and I get a number. And this turns out, with the right normalization, to be an integer, or well, if it's or a certain rational number with a fixed size of the denominator. So when I was writing my PhD, I was interested in bounded cohomology. There's a way to interpret this as a bounded cohomological invariant. And one of the things, if you interpret it via bounded cohomology, it comes out right away, that is that you have a kind of a generalization of the Milnor-Wood inequality, a Milnor-Wood type inequality for this invariant. And it satisfies that in absolute value it's always bounded, and again this depends on the right normalization, so the exact bound is not really important. It's some constant in terms of the Euler characteristic of the surface and the rank of your group G. Okay, so if you have such a bound, and this is also something which quite generally, in a sense, in a slightly different context, Bill suggested in this paper on characteristic class and discrete subgroups of Lie groups, you can look at the level sets of this invariant, and in particular the level set where equality is attained here. And this is what's called in this situation the space of maximal representations. So we take the level set of the maximal possible value our invariant can attain. This is a subset of the set of all homomorphisms. And we call that the space of maximal representations, and I will write hom max of pi 1 of sigma to G. Okay, so now, of course, you may wonder, why do you want to look at that? And the reason lies basically in Bill's thesis. So why would you expect this to be an interesting space? Well, Bill showed in his thesis that it's an interesting space if G is the simplest simple Lie group of emission type, namely PSL2R or SL2R. So let's write Goldman's thesis. So he proved several things, and I just want to highlight 2 of them. So if G is PSL2R, then the set of maximal representations consists of representations which are discrete and faithful and preserve the orientation of the surface. So here we can say immediately a bit more about that. If we have a discrete faithful representation of pi 1 of sigma into PSL2R, it acts on the hyperbolic space, and the quotient is a surface with a hyperbolic structure. So he showed that a maximal representation in PSL2R are precisely holonomies of hyperbolic structures. On sigma. This is one thing. The other thing he proved, and in this case for where G is PSL2R, I mean this invariant is the Euler number of the associated S1 bundle. He showed that this is in a sense the only topological invariant you need to distinguish the connected components of the space of all homomorphisms. So tau distinguishes the connected components. Okay, so I was a graduate student and working on maximal representations. At that time, I mean, Bill's webpage looked different than today's. His thesis was not on his webpage. His thesis was not, I mean, was referred to, but not available. So basically our first contact was by mail. So I asked Bill whether he could send me a copy of his thesis. And so I got a copied paper copy of his thesis with a very nice letter, which somehow was, I mean, very encouraging for a young mathematician. So why was I interested in this thesis? Together with Mark Burger and Alessandro Iazzi, we were studying the spaces of maximal representations into any Lie group of Hermitian type. And actually the first thing we wanted to show is that basically whenever you have a maximal representation, it's just given by rank of G copies of representations in SL2R. I wanted to show a very strong rigidity theorem, which we, I mean, while trying to do so, realized is not true. And actually there's something much more interesting happening, namely that you have an interesting space which is not just Teichmüller space, but has some of the properties, I mean, some of the things Bill showed. So this was joint work with Mark Burger, Alessandro Iazzi. If you have a maximal representation, then it's always discrete and faithful. So it's always an embedding of your fundamental group of the surface into G with discrete image. So now basically what I want to address, and this was a question which somehow from after we were working on that, which really bothered me for many years, to try to get not just that it's discrete and faithful, but to interpret these maximal representations in some way as holonomies of some geometric structures. So that's basically one of the questions I want to address, which is, I mean, I want to address it in a slightly different way than Nigel Hitchen addressed it in the last talk. So are maximal representations holonomies of some geometric structures? Okay, so the first, before we go more towards addressing this question, I want to give you some examples, because when you try to do that, you try to work and try to look at examples and try to work it out for examples and try to get some intuition about the general case. So let me start with the following example. So a priori, it's not always so easy to write down an explicit representation of a surface group, but we know very well how to do that in PSL2R or also in SL2R. So the first examples we want to discuss all come from SL2R representations, and the first comes from taking SL2R and taking the irreducible representation in even dimensions, which lands in the symplectic group, the subgroup of SL2NR. And then we precompose with a discrete embedding of the fundamental group of the surface into SL2R. And I call this rho irreducible because it comes from the irreducible representation. This you can compute very explicitly. This is an example of a maximal representation. It's a very important and specific one because it's also an example of a representation in the Hitchin component for SP2NR. So there's in the set, in this space of maximal representations for the symplectic group. The symplectic group is the only group which is both of Hermitian type and a split real Lie group. So inside there is a special connected component, which is the Hitchin component. And which is just defined as, I mean, Nigel Hitchin defined it like he defined it in the last talk using Higgs bundles, but I mean one description of it can be given as the connected component in the space of representations or in the space of maximal representation of rho irreducible. Okay, so for later purpose, I want to somehow say one more word about how you get the irreducible representation, which I mean, everyone knows, but because I want to use it later. So you get the irreducible representation by looking at the action of SL2R on R2 spanned by two variables x and y. And then you can look at the induced representation on homogeneous polynomials of degree 2n minus 1 on x and y. And this is a 2n dimensional vector space with a symplectic form. Okay, so this is one example. So let's describe a second one. So for the second one, I again use a representation of SL2R, but a different one. So I can look at R to n as a symplectic vector space. I can get it in the following way. I take a symplectic vector space of dimension 2, take the tensor product of an orthogonal vector space, so a vector space with a positive definite orthogonal form of dimension n. And if I do that, I get an induced representation of SL2R into SL2R times ON, which via this naturally sits in the symplectic group SP2NR. And I can pre-compose this with a discrete embedding. I call this rho diagonal. Why? I mean, it's not so clear from this perspective, but this is the representation with factors through embedding SL2R diagonally in a copy of n copies of SL2R and embedding this in to the symplectic group. But I want to, so the diagonal SL2R in here has a big centralizer, which is this ON. So this is also a maximal representation. And this is not in the Hitchin component. So in particular, from these two examples, you already see then if we go from G PSL2R to G, a different Lie group of emission type, the characteristic invariant will not distinguish connected components. So let me look at example 2 prime. So here we take a representation of pi1 into SL2R and then embed SL2R as into SL2R cross ON when we take the identity in ON. Can twist this example by a representation of pi1 of sigma into ON. And you get another class of examples. So these three classes basically give you, if you're not interested in small n, give you basically everything you need to know about maximal representations. So there are results on the number of connected components. So let's connected components of the space of maximal representations. And let's just write it for the symplectic group, sp2 and r. So there's precise count of the number of connected components, which goes through methods from the theory of Higgs bundles. There's a paper of Garcia Prada, Goten, and Mundert Riera, who show that if n is bigger or equal than 3, then the number of connected components is 3 times 2 to the 2g. And basically, all these, every representation into sp2 and r with n bigger or equal than 3 can be deformed to one of these examples. So you might wonder why there are 3 examples, but here I have 3 times 2 to the 2g. So the 2 to the 2g comes from the fact that here we take a representation into SL2R. And if you have a discrete embedding into PSL2R, there are 2 to the 2g possibilities of lifting it to SL2R. And then there's either it can be deformed to the reducible one, so it's in the hit chain, or it can be deformed to this diagonal one, or it can be formed to a twisted diagonal one. So something very interesting happens when n is 2. This is, again, a result by Goten using theory of Higgs bundles. The number of connected components is not what you might first expect. So there's more connected components than the one we see here. So there's 3 times 2 to the 2g minus 1 connected components plus 2g minus 3. And these 3 times 2 to the 2g minus 1 connected components again come from these 3 constructions. But there are 2, these are exceptional components. And in these components, every representation is Sierski dense. So in particular, you have no way of getting it by taking a representation of SL2R and embedding SL2R. So I want to give you a third family of examples which give you representations in these connected components. So these are called hybrid representations. We construct them in joint work with Olivier Guichard. And it's again the construction is again inspired by work of Bill. So there's a paper of Bill Goldman, Misha Kapovic, and Bernhard Leb, where they construct representations into SU1n with different Toledo numbers. And the way they do it is that they take representations into different SI2s and glue them together. So that's precisely what we want to do here. So let's look at a surface sigma, then has some topology. If we have a simple closed separating loop gamma, which separates the surface into sigma A, 2 subsurfaces sigma A and sigma B, then the fundamental group of sigma can be written as the amalgamated product of the fundamental group of this subgroup, amalgamate over the cyclic group generated by gamma, the fundamental group of sigma B. So in order to write down a representation of the fundamental group of the surface, I can write down one representation on one side, one representation on the other side. If they agree on gamma, they fit together to form a representation. And there is actually a way of a gluing theorem, which we prove with Mark Burger and Alessandro Iozzi, which also says that if the 2 representations are maximal, then the glued representation is maximal. So what do we want to do? We want to look at a representation which we get by taking the 2 nice representations we know, the reducible one and the diagonal one, put one on one subsurface, and put the other on the other subsurface, and then glue. There's a slight problem with that because you can't glue them. If you have something which lies in the hitching component, here the irreducible representation, the hyperbolic element will go to one which has distinct eigenvalues. If you lie in the diagonal, it has the same eigenvalues by definition. But basically, we can deform this diagonal representation by moving in the Teichmüller space, so that we get something which is not diagonal anymore, but deformed in this SL2R to the n, but which ends up with the same holonomy as the hitching, as the irreducible representation. So we deform this slightly, we can glue. And this gives us another example of maximal representations. And so if n is equal to 2, then these row hybrid representations lie in the 2G minus 3 special connected components. And you can get, by varying which piece of how much Euler characteristic you give to sigma A and how much Euler characteristic you give to sigma B, you meet each of these 2G minus 3 connected components. And the other thing you can analyze is if n is bigger or equal than 3, you can also make this construction. So this construction is not specific to SP4R. Then any hybrid can be deformed to the diagonal representations. So there you don't get anything else, but it will turn out to be useful as well. Okay, so now you basically have plenty of examples of maximal representations. You can deform them. Anything deforms to one of these you see on the board. So now I want to come back to this question regarding geometric structures. And of course, what do you do when you don't know how to start thinking about the problem? You try to see, is there a simpler case where people thought about the problem already? And so when we were together with Olivier Guichard trying to address this problem, we've said, okay, so let's do first one reduction. Let's first look at the simplest example of maximal representation we have, which is not just a holonomy of a hyperbolic structure. So this is SP4R, and it's this irreducible representation. It has a lot of structure. And the nice thing about this irreducible representation, it lies in the Hitchin component. So there is some inspiration you can get from other Hitchin components, namely again from the work of Bill and the work of Bill together with Choi, who gave a nice geometric interpretation of the Hitchin component for SA3R. Forget for a moment, it's not a Lie group of Hermitian type. It doesn't fit in this picture, but perhaps you can learn something from it. So if you look at the Hitchin representation, Hitchin component for SA3R, then so work of Bill on convex reproductive structure, and then the joint work with Choi on the closeness tells you that this is actually equal to the space of convex RP2 structures on sigma. So let me just draw the picture, because this is really what, in a sense, inspired us. And this goes, in some sense, back also to a discussion I had with Bill in 2005. So we had some exchange of papers in 2004. Then in 2005, there was a conference organized in Basel and Strasbourg, to which Bill came. So that was the first place we met. And that year we met a second time in Madrid at a small workshop Oscar Garcia Prada was organizing. And so I had started thinking about that. And to understand what geometric structure you could associate to the Hitchin component for SP4R. And so Bill said, well, think in terms of polynomials. And so what happens if you think in terms of polynomials? So the first thing you have, in a sense, you can write down, now I first write it down for SL3R. For SL3R, you look at homogeneous polynomials of degree 2 in x and y. So this is R3. And you get a map from RP1 into RP2 in the following way. So if I think of a point in RP1 as parameterized by t, but I really think of t as being the polynomial x plus ty, then I get a map which sends this to x plus ty squared. Right? So I get, when I look at this map, I get some nice quadric in RP2. And how do I see the convex on which I model the surface? It's the interior of this domain, and one way to think about the interior of this domain is to say, well, I take this curve, I remove it, I have two connected components, but another way to think about it is actually that instead of just looking at the curve, I look at all its tangent lines. And if I look at all its tangent lines, everything in the complement sits on one tangent line, so it goes away. If I remove all the tangent lines, I really just stay with omega. Okay, so now we want to apply this. We want to apply this idea for in one dimension higher. So for SL4R or SP4R. So what do you have here? So with thinking in terms of polynomials, you write down the same map. Just now it goes into RP3. Take t and you send it to the polynomial x plus ty to the 3. So what you get is a curve which is this twisted cubic. Where you have a codimension 2 object. And now you do the same, you try to do the same thing. You remove all the tangent lines. So take remove the surface, so it's a nice ruled surface spanned by tangent lines. Then what do you get? So again, in terms of polynomials, you get, if you look at the complement, let me call this the surface, let me call this k phi. So the complement RP3 minus k phi is what in terms of polynomials? So here you have a polynomial which has a triple, one root of multiplicity 3. A point on the tangent surface is a polynomial which has a double root, so root of multiplicity 2. So you end up with the roots, with polynomials where there are no multiple roots, and there are two things which can happen. You have the polynomials where you have 3 distinct reroots, and you have the polynomials where you have 1 reroot and a complex conjugate pair. So. And now, I mean, how do you think of these terms? And that's, in a sense, something which I learned from during these discussions in Madrid. A reroot, you think of it as a point on RP1, and the complex conjugate pair, you think of it as a point in the Poincare disk. So you see from this decomposition, you see 2 things. So the first is, if you look back at your surface group, and you look at it, so let's call this complement omega, you look at its action on omega, it's like the action on 3 distinct points on the boundary, or the action on a point in the hyperbolic space and a point in the boundary. So this action is properly discontinuous and co-compact. And you also know, you see what the quotient is. So the quotient, it has two components. So one is this one here. You can identify it with the unit tangent bundle of the surface. And this you can almost identify with the unit tangent bundle of the surface. If you had ordered triples, then you could identify it with the unit tangent bundle of the surface. So here you mod out by the cyclic permutation. So you have the unit tangent bundle of the surface mod out by the cyclic group. So looking at just the irreducible representation and thinking of it in terms of polynomials, you see that you get some nice domain in projective space on which your group acts properly discontinuous and co-compactly, and such that the quotient space is really basically the unit tangent bundle together with a projective structure. And so analyzing this picture now, not just for the irreducible representation, but also for any deformation of it, what we got in this joint work with Olivier Guichard is a characterization of the Hitchin component for SP4R or for SL4R as certain projective structures on the unit tangent bundle of the surface. So we focus on this one component, and basically with some additional structure which you get by looking at the foliation, which you get by the real root, which can vary. And then every foliation, so you see a convex, in every leaf you see a convex domain. So I don't want to go into detail. So we describe the Hitchin component of representation into SP4R as convex foliated projective structures, and to get in the symplectic group you have a certain contact structure which is preserved. If you remove the contact, you have SL4 here. So this one, when we got that, we were very, very happy, because somehow it was another example where you have an interpretation of one of these higher Teichmüller components. So one component, the Hitchin component, which also is one component of the space of maximal representations, in terms of some very explicit geometric structure on the surface. Okay, but it's obvious the right-hand side is two. Which one? This one? This one?
Next board.
This one? No, I mean a priori not. I mean really the hard part. So the soft part, in a sense, using characterizations of elements in the Hitchin component due to François, is to go from something in the Hitchin component to some projective structure. That's, in a sense, the soft part, and I basically, in the special case, explained to you how to do that. The hard part is really to say, well, if I have this projective structure, then I get the holonomy, and of course the holonomy gives me a representation into SL4R, say, or if I take the contact into SP4R. But to actually pin down that it lies in the Hitchin component, that's actually quite tedious and involved. So that's the that is really quite technical. And this is also so far the only case besides, basically Teichmüller space, the Hitchin component for SL3R, and the Hitchin component for SL4R or SP4R are the only cases where we have this kind of very explicit description. So in terms of a deformation space of geometric structures, where the deformation space we look at is really completely characterized by geometric properties of the geometric structure. So what I want to explain now shortly is that the other part, somehow the softer part, that you can get for any maximal representation. So if I have a maximal representation, I want to give you a construction of a domain of discontinuity on which this maximal representation, the surface group acts properly, discontinuous and co-compactly, and where then somehow the quotient is naturally endowed with a projective structure. Okay. Okay, for the more general situation, that rho is not necessarily the Hitchin component, but any maximal representation in the symplectic group. So that's so G, the symplectic group, SP2NR. Basically, you want to make the same construction by removing, finding an equivalent thing of this tangent surface, which we described here very explicitly, but somehow now we can't describe it as explicitly in terms of polynomials. And this relies, that we can find this tangent surface relies on a characterization of maximal representations. Which is due to, partly in this work with Mark Burger and Alessandro Iozzi, and especially for the symplectic group, and the part in joint work with Mark Burger, Alessandro Iozzi, François Laborie, and myself. So if you have a representation of the fundamental group of your surface into the symplectic group, then this is maximal if and only if you have a map from RP1, which I want to think of as the boundary of the fundamental group of the surface with the natural action of the surface group, into, well, where does this tangent, if I think of the tangent line here, a tangent line here is a two-dimensional subspace of R4, and you can check using that this curve here is Legendre, meaning that this tangent line, this two-dimensional subspace, is actually a Lagrangian subspace of R4. So you go into the space of Lagrangians. So this is continuous row equivariant, and as another important property, it's triple positive. And let me say what this means. So on RP1, we can make sense of a positive oriented triple. If I have 3 points x, y, and z, I call x, y, z positively oriented if I read them in this orientation going along the circle with its natural orientation. And in the space of Lagrangians, there's also a notion of positivity or triple positivity, which comes from the Maslov index. And let me shortly describe it. So let me draw a sketch of a picture. So I have one Lagrangian, which I call L plus, one Lagrangian, which I call L minus, and I have a third Lagrangian L. And I assume that they are transverse, so that L plus and L minus don't intersect outside of 0, and L doesn't intersect L plus, doesn't intersect L minus outside of 0. Then I can use L plus and L minus, these are half-dimensional subspaces, to span my symplectic vector space. And using this decomposition, I can define a quadratic form on R2n. So let me define it. So alpha of a vector v in R2n is the following. So I write v as v plus v minus with respect to this decomposition. And now I have my symplectic form, and I can evaluate the symplectic form on v plus, v minus. This is a quadratic form on R2n. And so if I have 3 Lagrangians, I can take this quadratic form, and let me write it here. So I can take this quadratic form and restrict it to my half-dimensional subspace. And then I can look at its signature. And that's the Maslov index of L plus L minus is the signature of alpha restricted to L. And so I call L plus L minus positive if this mu is equal to the maximal possible value it can have, which is n. So you can easily check this quadratic form is of signature nn on R2n. Okay, so now that the map is triply positive means if I take a positive oriented triple on RP1, I get 3 Lagrangians, I compute the Maslov index, and this is always n. Okay, so now in the first step to find the geometric structure, we will actually just use basically the first property, not the stronger property of the positivity. And this is, just to put this into context of things which we might hear later this week, this maximal representations into SP2 and R are examples of Anosov representations with respect to the stabilizer of a Lagrangian. And the construction I'm going to describe is a more general construction which you can do for any Anosov representation. It doesn't use the triple positivity for the moment. So what do we want to do? We take this map and we want to use it to find the domain of discontinuity. So, and basically just follow the example we understood. So we have this map and we want to think of, we get a family for every point t in RP1, we get a Lagrangian, and the Lagrangian gives us a certain subset of projective space, namely all the lines which lie in this Lagrangian. So what I want to consider, so given this curve from RP1 into the space of Lagrangians, you consider a subset of RP2n minus 1, which is, let's write it. So the complement of a certain set k phi, which is, a generalization of this tangent surface in this more general case. So what is k phi? So it's a union for all t in RP1, so for all points on the circle. I take my Lagrangian subspace phi of t, so this half-dimensional subspace, and I take all lines which are contained in it. This removes an RPn minus 1 for every point on the circle, so I have a circle of RPn minus 1s, which I remove. So this is my domain omega, and then the statement which we prove with Olivier Guichard is that if I have rho, so if I have a maximal representation rho, or more generally an Anosov representation, then if I look at the action of pi 1 of sigma on this set omega, this is properly discontinuous and co-compact. So what do we get? So it's co-compact, so if I look at the quotient, I have a compact manifold, M, with a projective structure. So I have that every maximal representation is somehow the holonomy of some projective structure on a compact manifold. Of course, it's not that nice, because it's far from giving a really geometric description because I can't even tell you at that moment what is M. It's some compact manifold. Of course, it's not the surface because the dimension is 2n minus 1. So it's a high dimensional compact manifold with a projective structure. So what I want to basically illustrate in the last part of the talk is how you can determine the topology of that manifold. So so let me write it as theorem again with Olivier Guichard. So if rho is a maximal representation, into SP2NR, then rho is the holonomy of a real projective structure on a compact manifold M, and M is topologically, so it's homeomorphic to the total space of an ON mod ON minus 2 bundle over the surface sigma. So in fact has some relation to my surface. So in order to see that, let's look at an example, and this time I want to take the other somehow easiest and standard example, the diagonal representation. So if we look at the diagonal representation, I told you one way to think about it is by thinking of R2n as R2 product an orthogonal vector space of dimension n. And if you think of it in this way, then it's very easy to write down what this map is. So the map phi, well, we have to take a line in R2 and associate to it an n-dimensional subspace. And so what you do is you take T, or what the map does, it takes T and sends it to T tensor W. That's the Lagrangian. So now, what does it mean now to remove all the lines in here? So it means in this R2n, you remove all indecomposable vectors. You have every vector of the form T tensor W. And what you're left with is all indecomposable. You remove all indecomposable vectors, you're left with the decomposable ones. So omega is the set of, so the lines which are spanned by vectors V, where V is of the form T1 tensor W1 plus T2 tensor W2, where T1, T2 are linearly independent, and W1 and W2 are linearly independent. So in this situation, we have a very, very good understanding of how this domain looks like, because we have this, we land in this group SL2R cross ON, which preserves the whole picture, and this group actually acts on this space transitively, and you can compute very explicitly what the stabilizer is. So what is omega as an SL2R cross ON orbit? Well, so what do you get? I mean, you have the two-dimensional subspaces spanned by T1 and T2 and W1, W2. You can act by an orthogonal transformation on T1 on R2. But then you have to somehow act also by the same orthogonal transformation on W1, W2. So you have a diagonal SO2. And then you have the orthogonal complement of the span of W1, W2, on which you can do whatever you like. So this is an ON minus 2. And so if we look at omega mod pi 1 of sigma, our quotient we are interested in. So we have this on pi 1 of sigma. And now if we project to the first factor, we get the projection to SL2R cross SO2 on pi 1 of sigma, which is our surface sigma. And the fiber will just be the ON, mod ON minus 2. Okay, so for the diagonal situation, it's very, very explicit, and we can very explicitly determine what the topology is. So now you want to try to take the diagonal representation and try to understand what is the topology for the other situations. And I explained to you when I gave the examples, well, the first remark is, if I can tell you what the domain is for one representation, I know it for the whole connected component. So the domain for two different representations in the same connected component will be homeomorphic. So I just have to find the answer for one example in each connected component. And I gave you the example. So what are the ones which we have to deal with? So we have to deal with with three cases. The first is the easiest. We have to deal with twisted diagonal ones. Twisted diagonal ones, you do the same. You basically do the same construction. You just act also on the ON factor, but that's basically the same. So twisted diagonal is fine. Then what we are left with? We are left with hitching for n bigger or equal than 3, because for n equals 2, we understood precisely what it is. And we are left with hybrids for n equals to 2, because for hybrids for n bigger or equal than 3, they deform to the diagonal 1, so we know what the answer is. So now we want to understand what these are, and so I'm not going to give you the details of the proof, but just the main idea. And in a sense, it's again something inspired by what Bill did for convex reproductive structures. You try to analyze this thing over the compact surface by understanding smaller pieces, and the small pieces we understand well for surfaces are pair of pans decomposition. So basically the strategy is cut and conquer and then glue together. So now we have to understand how can we cut. And this is this I want to explain shortly. So cut. So if I have a surface, if we want to cut it into simpler pieces, we start cutting by simple closed geodesic. So gamma simple closed geodesic, and it's often quite useful to think of it instead of thinking of it on the surface, or think of it on the universal cover. If I have a closed geodesic, I have its lift, one lift which goes between the fixed point of the element gamma, and then I have the other lift. So, okay. So now I want to, here I have my, instead of this, I have my domain omega. If I think of a separating or simple closed geodesic, it cuts the universal cover in two pieces. And so now I want to construct a hypersurface which cuts omega in two pieces. And this is, in a sense, inspired by two things which are in different areas of Bill's work. So one, his work on convex reproductive structures, where he analyzes and explains how to glue convex reproductive structures. And the other is his work on proper affine deformations, where he constructs crooked planes, or interesting hypersurfaces to somehow analyze structure. So what's the hypersurface? And let's define it. So if I have two Lagrangians L plus and L minus, so for example the images of the fixed point, I explained to you that we can construct this quadratic form. And what we just do is we take the set where the quadratic form is 0, and then projectivize it so that it lies in Rp 2n minus 1. So this gives us a hypersurface. And now one has to understand why does it cut. And for this, there's the key proposition really now uses that we are in a maximal, in the situation of maximal representations. Then we have phi, this triple positive map, right? Then the intersection pattern of the hypersurface, which we would associate to phi of x prime, and the hypersurface we associate to phi of y prime, is precisely the intersection pattern we see in the hyperbolic plane. So they do not intersect, or they do intersect if and only if we have x prime, the geodesics determined by x prime, and y prime intersect. So the hypersurfaces upstairs in projective space mirror the same combinatorial intersection pattern as the simple closed geodesics on the surface. And so if you have a decomposition of the surface, you can decompose your domain of discontinuity over it. And now you can basically try to, you have to glue the pieces in order to understand these two cases. So for hybrid for n equals 2, you have a piece which comes from the domain of discontinuity for the Hitchin representation, and a piece which comes from the domain of discontinuity for the diagonal, and you glue them together and you show that the pieces were O2 bundles, actually two SO2 bundles, and if you glue them together, you show that you get again two SO2 bundles, where the Euler characteristic tells you which hybrid representation you have. And in order to analyze it for the Hitchin component, actually you do the same. You again use hybrid representations, so you understand the topology for the hybrid representations, and then you go back showing that the ON mod ON minus 2 bundle, which you get as a quotient manifold for the Hitchin representation, is exactly the same. So let me finish with two short remarks. So one is there is very interesting work in progress by Daniela Alessandrini and Chongling Li, who somehow showed that you get projective structures both for the real symplectic group and the complex symplectic group for maximal representations using the theory of Higgs bundles, and you get some additional information out of that. And there's some other, I think, interesting work, which is also nice connection, again, between me and Bill, of two of our graduate students who use these hypersurfaces to give a geometric construction of Schottky groups and Schottky representations in the symplectic group. So I want to end with the mathematical part of the talk here and come to the birthday presents. So, I mean, this somehow nice geometric structures are somehow a bit of intellectual birthday present, but you can't put them in your hands. So I brought another interesting geometric structure for you to put in your hand. So it's a geometric structure, a Euclidean structure on the surface, which develops on the plane. So so this is and there was at some point in mathematics, there was some time where some people refused to publish papers and had this with some community mathematician who had this somehow tradition then to give each other presents, papers as a present, so out of their drawer. So I also brought you, well, I don't refuse to publish it, but I brought you a secret paper as a present. So happy birthday.
Thank you very much.
Crystal clear talk. So.
Thanks.
Thanks again.
Thanks.
Okay, so we'll break for lunch, and let me just very, very quickly say that by my count, we have about 5